let's finally put it all together and wrap this problem up. Namely, we're going to find the population variance, the sample variance, the population standard deviation, and the sample standard deviation for this stats exam problem that we've been working on. So let me just recap real quickly. We found the deviations, we squared them because otherwise when you add them all up they're 0. So we squared them to turn them all positive, then we added them all up and we got 1756. And then we took a moment to kind of take a breath and realize, hey, that 1756, that's the beginnings of something very powerful called the variance. Namely, it's the numerator in the variance formulas. So 1756 is the sum of the deviations squared. And then we realized, okay, variance and standard deviation have a whole bunch of very important relationships and definitions that we need to make sure that we have written down, say, for our notes for exams and the final. And we have all that information, but that's where we're at. So now we're going to find the population variance. So according to the formula, it was 1756 divided by n being the population size. So if you treat this data set like it's a population, which of course it isn't, but pretend that it is for a second, there are 10 data points here. So you're going to divide that 1756 by 10. So we take the 1756, we divide it by 10, and we get 175.6. Now keep in mind the unit's going to be points squared. So it would be whatever unit you have for your data set squared, which in our case was points. All right, and again, don't worry about the interpretation part, but you write the point squared just to kind of remind yourself of how crazy this is. Like, it's just weird. And that's because we don't use it for that application. We don't use the variance to interpretation or for interpretation. We use it for other things later on. Now the sample variance is divided by n minus 1. So instead of dividing the 1756 by 10, we divide it by 10 take away 1, which would be 9. And again, that's just to compensate for the fact that this is a sample, not a population, so we don't know as much about it. That means that we are dividing by 9, which gives us 195.11111 repeating points squared. And if you don't believe me, let me take 1756, 56, and divide it by 9. Lo and behold, I'm correct. All right, those are the variance values. Now, what would the standard deviation be? Well, remember that relationship. It's really important. This blue one I highlighted in blue right here. The standard deviation is the square root of the variance. So if you have the variance, like we do in our problem, you would just take the square root of it to find your standard deviation. Okay, so if I know that the variance, let's say for the population, was 175.6, that means that the standard deviation would be the square root. So I hit second square root, and then 175.6, enter. And I get 13.251. Similar, the sample one would be the square root of 195.1111111. I'll just throw a lot of ones in there, which is 13.968. All right, so the population standard deviation is 13.251 points, not points squared, because the square root undid the squaring that we did in the formula. So it was deviation squared, but because we took the square root of the squaring, it undoes the point squared and leaves just points. It's a little algebra trick. Well, this is going to be way more useful, this whole points business, for actually interpreting, right? We could say, I expect to score within 13.968 points of the mean, right? That makes a lot more sense. But let me show you one other thing. These two values are not found, the variance values are not found with the calculator, but these two values can be found with the calculator. Let me show you that real quick. So if you recall, I have the data set sitting right here in L1. So when I go to Stat, Calculate, one variable, and I go down to Calculate, you can see, look at the SX. X, by the way, just means data, so don't worry about X, right? So the standard deviation, the sample standard deviation of X's, of data, is 13.968. Look familiar? Because it's the same number we have. And sigma is 13.251. And it says it right there, sigma x. So both of these values can actually be found with the calculator. So you never need to find them by hand. Instead of saying can be, I should say should be found with the calculator rather than can be, because we do not calculate standard deviation and variance by hand. So wait a second. If you found these values with the calculator, right, say you didn't do that table on the other page, which is going to be, quite frankly, the way this is going to work every single time. You're never going to do that table over there. So if you're not going to do the table, how would you have gotten these values here? Well, all you have to do is take the number the calculator is giving you, 13.968, and square it. And you get 195.1. Now we've lost some accuracy there, right? But it still works, right? And then if you want 13.251 and you square it, press enter, you get 175.6 roughly. Now you'll notice I'm losing accuracy at the first decimal place. Let me just really quickly teach you a way around that. Suppose you don't want to lose accuracy for some reason. Well, the last time I ran one variable stats, the calculator automatically, every time you run one variable stats, stores the information. It stores every one of these values in its memory until you run one variable stats again with a new data set, and then it forgets them all. And it stores them in the variables menu. So if I go to variables and I go, hey, look at number 5, statistics. That's the name of the class. That's a good sign. So I hit number 5 and then see number 3, SX. So if I hit that, SX, and I hit squared, it actually knows the standard deviation S with all the decimal places. So 13.968, yada, 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 yada. I press enter, and there it has it. I could do it again for the other one. So vars 5, sigma x, and squared. And there you have it, 175.6. So even if you use your calculator to come up with these numbers for variance and standard deviation, it'll still work. Most of the time you don't need this whole vars thing. I'm just showing it to you just in case you ever want to use it for any reason. So let me type up what we just did. 1 second. There we have it. So again, you don't have to necessarily do the vars thing. As a matter of fact, sometimes in my math lab or my stat lab, they expect you not to have used it, so they expect you to lose decimal places of accuracy. So watch out when you're in my stat lab for how many decimal places they want. When me personally, if you're doing a worksheet or an exam by hand, then you can keep as many decimal places of accuracy as you like. I'm always fond of more accuracy, not less, but for various reasons, the computer programmers might have reasons for why they didn't necessarily require all the decimal places of accuracy for my stat lab. So just watch out for that. But if ever you want all the accuracy, this is how to do it, right? You go to one variable stats, you find your sigma or your S value, then you square that value. If you want to, you can use vars, then number 5 statistics, then either number 3 for SX or 4 for sigma X to get the calculator stored version value of S with all the decimal places before you square it. All right, so that's how to find that by calculator, which is very useful. That's the way you're going to do it. That's the way you're expected to do it. Never, never, never do it by hand again. That was a one-time thing to get you to understand how this works. Now, of these two values, the variance and the standard deviation, or which of them, the variance, population variance or the sample variance, the population standard deviation or the sample standard deviation, was more appropriate for our situation? Well, because the problem says it's a sample right here, that means that we want the sample values. So the sample standard deviation and the sample variance, because the data set was a sample in the first place. That's pretty easy. So it's just a little reminder of what parameters and statistics are. So I guess I can, that's right here. Are these values parameters or are they statistics? So let me make a note. Note. S and S squared are statistics because they are from a sample. Just a little reminder of that one definition of statistics. Speaking of reminders of that, what about the answer for part C right here? Was that a parameter or was that a statistic? Well, because it's a population value, population goes with parameter. So that would be parameter. Done with that. Now, one of the most important pieces is the interpretation piece. This is key. How do we interpret the mean and the standard deviation in the context of the situation? All right, well, that's a very big deal, and I got at it right here in the bottom, right here. So it's the give or take that we want. That give or take from the mean, that is key, right? So in other words, most of the data falls within a standard deviation or two of the mean. We'll get at the or two part later, but for our purposes right now, we're going to stick with just a standard deviation of the mean. Okay, so what does that mean for our data set? So we have a mean of 74, just a little reminder. The mean on this data set was 74. So if you were a student in this class, you'd expect to score a 74. That was the average for the class. But you don't really expect a 74. What you expect is to be kind of around 74. And the thing is that mathematicians don't like that kind of around language. They want to be more precise than that. So what they say is we expect to be 74, give or take 13.968. So if you were a student at random from this class, you'd expect to score 74 points on this exam, give or take, right, around that 74, 13.968. In other words, we expect most students to score 60.032 points to 87.968 points, somewhere in there, somewhere between those two values. Now I got those two numbers by taking 74 minus 13.968 and 74 plus 13.968. Right? I'm building kind of a window where most students are going to fall. And what do I mean by most? It varies on the data set, but let's start with like 50%, right? Half of the class-ish should fall in there, provided the data set's not really skewed and really messed up. Which leads us to one more point, the last point of this example, which is, okay, so if most students fall in there, where's unusual? What counts as unusual? A weird score. Okay, well, to do that, we need to define what unusual is going to mean. Unusual is going to mean any data point that is above 2 standard deviations to the good or below 2 standard deviations to the bad. So if you're past 2 standard deviations, up on the top, or past 2 standard deviations on the low side. I realize this picture is a little bit out of order, but bear with me here. So you have your mean in the center, and anything that's above 2 standard deviations above that mean will be unusual. Anything that's 2 standard deviations below that mean will also be unusual. Sorry, I mean below 2 standard deviations below the mean. Let me draw the picture 1 second. Here we have it. So the mean is in the center. You figure 1 standard deviation is halfway between the red and the blue arrow on this side and the red and the blue arrow on that side. So 74 is in the middle for our particular example. And then you want to add on 2 standard deviations, not just 1, but 2, and 2 standard deviations taken away. You want to subtract. That gives you your usual area, right? So most students are going to fall within 1, but usual students are going to fall within 2. Right? So it's a little weird. So most students are between 60 and 87, but the usual area would be anything past 2 standard deviations away. So you want to take the mean, 74, and you want to subtract away 2 standard deviations. And then you want to add up 2 standard deviations. So I did, and you can see the calculation I did, 74 minus 2 times 13.968. That got me 46.064. Then I did 74 plus 2 times 13.968. And that got me 101.936. So any scores that would be below 46 or above 101 would be unusual. And that means that we did not have any weird scores or any unusual scores because we had nobody in our data set below 46 nor above 101. And just real quick, I made a note of most is within 1 standard deviation. Usual is within 2 standard deviations. So therefore, unusual will be more than 2 standard deviations away from the mean. So within, or I should say within or equal to 2 standard deviations. So 2 itself actually falls in the usual zone. It's past 2 standard deviations, more than 2 standard deviations away, that counts as unusual for our purposes. And keep in mind, this is not set in stone. This is just kind of a rule of thumb, right? Which means it's not a perfect rule. This is just kind of how the standard interpretation goes, but there might be reasons in your data set for whatever reason not to make it 3 standard deviations or to make it 1 or whatever. But for our purposes, for our course, we're going to stick with 2 for the most part. So 2 standard deviations and within is usual, and past 2 standard deviations is unusual. Past 3 standard deviations, well, actually it's not 3, it's less than 1%. So if you have less than 1%, that will be considered very unusual. We'll talk about that more in chapter 5. Less than 5% of the data, because these 2 green zones, even though they seem very large, are actually around 5% of your data for most data sets. So that will be considered unusual. This little bullet right here is going to come back a lot in chapter 5 when we deal with probabilities. So just keep that one in mind. For our purposes for right now, the top half is more useful. So just keep it all in mind. Perhaps put it on a note sheet. Hint, 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 hint. Put this on your note sheet and keep using it both through this chapters as well as chapter 5, and it'll come back in chapter 6 and 7 and so on.